Welcome to Lecture 12 of Calculus 3. In this lecture, we are going to introduce the idea of a double integral, but I'd like to start by recalling from Calculus 1 the definition of a definite integral in Calc 1. So let's do that first. Recall from Calculus 1. So let's let f be a continuous function on an interval. And as we know, the function doesn't actually need to be continuous to be integrable, but just for the sake of this argument, let's just say that it's continuous, a continuous function on some interval from a to b. And then let's consider the following. So if our function is continuous, then we can draw a nicer picture, right? So here's our y-axis, our x-axis, here's our a, here's our b, and maybe our curve looks something like this, the graph of our curve, the graph of our function, f of x. And we want to try to integrate this function, right? So remember what an integral does. It computes the area underneath the curve, right? Computes the area between the positive x-axis and the curve. So if the curve is above the x-axis, you get a positive number. If it dips below, then you get a negative number for that portion. But the idea is that the area under this curve is equal to the integral from a to b of this function f of x dx. All right, and we know all this, right? But we're just reviewing just to set this up. And so the idea of how we do this is that we make a partition. So we set this up, we let x naught equal a, and then we chop up our interval into pieces. And remember, they can be spaced out however we want. Usually when we compute these, we make a uniform partition, but you don't have to. So in the most general form, you make any partition where x equals a naught is the left endpoint, x sub n is the right endpoint. So this has n intervals in this case. And the only rule is that the partition points are ordered, right? That they're in order. So these are our partition points, and then we want to use these intervals, the n intervals that we've chopped up our interval a, b into, so it's now into n subintervals. We want to use these subintervals to draw little rectangles to approximate, rectangles or maybe trapezoids, but for the sake of this, let's do rectangles that approximate the height of our curve, right? So what do we do next? Well, next we have to choose a point that's going to allow us to compute the height of the rectangle. So the base of the rectangle is given by the partition, right? So there's the base of our rectangle. It's given by the partition. So, and we call that delta x sub I. It's always going to be x sub I minus xi minus 1. And this will be true for I equals 1 up through n, right? 1 through n. So that's the length of the base of this. And then we have to choose any point. So we can choose any point here. We'll call it xi star. Any point between xi and xi minus 1. It could possibly be the endpoints, right? But any point in the interval, including the endpoints. And then we use that point to go up and find the height of the curve, right? So we use this to draw our rectangle. I chose a portion of the curve that looked pretty flat there. But remember, the choice of the test point can dramatically change the height of this rectangle. And so this height over here is f at xi star. Right? And so then, what do? Well, now we compute the area of this sub-rectangle, this rectangle, right? So the area of that rectangle, call it a sub I. This is equal to the height of the rectangle, f at x sub I star, times the base of the rectangle, which is what we call delta xi, right? And the area of the whole thing is approximately equal to the sum of these a sub i's, right? So it's approximately equal to the sum as I goes from 1 to n of these areas, which is the sum as I goes from 1 to n of f of xi with a star times delta xi. All right, well, how do we make this go from approximate to exact? This is where the calculus comes in, right? Now we take a limit. So you take the limit as capital N goes to infinity. The result is that the intervals become extremely skinny, right? So delta xi goes to 0 for all I. And the end result is that if that converges, then that value is the area underneath the curve, and we call it the definite integral, right? And so this is our definition. It becomes a Riemann sum, right? Our definition. Integral from a to b, f of x dx is equal to now, exactly equal to the limit as n approaches infinity of the sum I goes from 1 to n, f of xi star, delta xi. It's got to be the same limit for any partition, right? So that's why we don't have to specify anything about the partition, but then provided, as long as the partition obeys the rules that we laid out, provided the limit exists. And this is exactly how we compute an integral, a definite integral in Calculus 1. Right? Remember that was called a Riemann sum. That's called the Riemann sum definition of the integral in Calculus 1. All right, well, let's try to expand this to Calculus 2 now. To do it in Calculus 2, we're going to have to make some more assumptions, all right? So let's suppose, again, that we have a domain. So let's suppose that R is a rectangle in the two-dimensional plane. So let's suppose that R is equal to, let's say, alpha, beta, cross with delta, gamma. So what does this notation mean? So this is going to be a rectangle, all right? This has to be a rectangle for the setup that we're doing right now, and we'll extend it to other shapes later on in this lecture, actually. But suppose this is a rectangle. This is in our domain space, so we're going to end up having a function of two variables. But let's draw the rectangle first so that we understand how this works. So it's in the xy plane, and the idea here is that we have our alpha and our beta in the x direction. So we have a closed interval down here, and then we have our delta and our gamma up here in the y direction. And so we can close off this rectangle, right, just by doing this. So we will always assume, by the way, that if we're given this in this cross notation, that it's in alphabetical order. So x first, then y. And if we move to 3 dimensions to make it like a box, a prism, then it'll be x, then y, then z in order. Okay, so those are the boundaries in the x direction first, then the y direction. So this is our region. The interior of this box is our region R. All right, and so now we want to, again, assume that we have a function defined on this. And let's just, for the sake of this argument, assume that the function is continuous. All right, so let's let f be a function of x and y. Let this be a continuous function on this rectangle. All right, and again, we can loosen this hypothesis that the function is continuous later on, but it'll help us for the sake of writing down the definition, right? So before we write down some kind of definition about what it means to be an integral, so we're going to compute an integral of this function f over this rectangle R. Let's think about how the function behaves on this rectangle. So it's going to take all the points from this rectangle. Let's shade this in just a little bit, just so we can see what we're working with. All right, so everything on the interior there, that's our rectangle. So what's it going to do? Well, the function is going to assign a third number, right? A height, a z value to each point in here. So really, what do we have? Over here, I'll draw, there's our x-axis. There's our y-axis. And then there's going to be a third component, a z-axis, right? And so, if I can get this correct, in the x direction, yeah, we're going to have, our rectangle is going to look like this. Something like that, right? And so then we can shade in here. I don't really want to do that, though. Okay, so it looks like this. This is our rectangle, and then our function itself is going to do what? It's going to take these points, and it's going to assign a height to them, and sitting above this, up in three-dimensional space, we'll have a surface, right? So who knows what the surface looks like, but this surface up here is going to be the graph of f. And remember that in Calculus 1, the integral measured the area underneath the graph, or between the graph and the x-axis, right? Now, the integral, whatever it is going to measure the volume enclosed underneath, in some sense, underneath. So, I didn't draw this very well. But it's going to measure the volume enclosed underneath the, there we go. So underneath the surface up here and the XY plane. So the volume of this thing, the volume is going to be equal to what we're going to call the double integral over the region R. Remember the domain down here, this is the region R, right? Of the function f of xy, and then the notation here is going to be dA. And so the reason for that is going to be the following. So how are we going to compute this? Well, the base has an area element now, not just a length element. Up here it was dx, dx because it's a tiny length element, right? Down here it's going to be dA because it's going to be a tiny area element. So here's how we're going to do it. And again, I'm not going to write down all the details because it's going to be very similar to the calculus 1 method. But the first thing we're going to do is we're going to partition both intervals. So we're going to make a partition of each the x and the y interval. So we'll make this xn. So our partitions are going to be then x naught equals alpha less than x1 less than x2 all the way up to x sub n equals beta. So we have n components in the x direction, and then we could have a different number potentially. Maybe we have a lot more up here or less. It doesn't matter. But we'll call these y1, y2, all the way up to y sub m, so that they're different. And we have these two partitions now. This is y0 it starts with. y0, y1, etc. So y0 is going to be equal to delta, less than y1, less than y2. And these work their way up to y sub m, which is going to be our gamma. That's the upper bound. All right, and then we're going to partition. So now we have two partitions, and they're going to work together to now partition the entire region R into sub-rectangles. So not just sub-intervals, but sub-rectangles. And so even though I drew so many of these dashes over here, I'm going to not draw as many when I actually break this up over here because I want to be able to see what we're doing. All right, but we break these up into sub-rectangles. And so the partition now, like I said, creates sub-rectangles. So let's focus on one of these. Let's pick this one. All right, so we can label these by their right and upper endpoint. So by this point right here. So this is going to be the rectangle. So this point right here is the point. Let's call it xi, yj. All right, and so that's the point in the corner, but it also identifies the entire rectangle, okay? And so this identifies, we'll say, identifies the rectangle Rij. All right, so now let's draw the same rectangle over here. So the rectangle is going to be somewhere like around here. This one's going to be Rij. And we're going to do the same idea, which is we're going to find the volumes of small prisms that sit above this. We're going to add them up, get approximately this volume, and then of course take the limit, right? So it's going to be very, very similar. So what we're looking for over here on the right-hand side now, in this picture with the graph, is we're going to draw above each one of these subrectangles, we're going to draw a little prism, and we just need to identify the height. So how are we going to do that? Well, the same way. We're going to pick any point, any test point in here. So the test point's coordinates are going to be xi with a star, yj with a star. All right, and then above those test points, we go up to the surface and we cap off our prism by using that height, right? So we use that height to find our prism. So this height right here is f of our test point, xi star, yj star. That's our height. And then the base, right? So the volume of a prism is the height times the area of the base. The area of the base is going to be determined by the partition over here in the domain space, right? So in the x direction, we'll have delta xi equal to exactly what we had before. I'm going to write this somewhere else down here. Let's write it over here. So our delta xi is going to be xi minus xi minus 1, and this is for I going from 1 up to capital N. Our delta yj, that's going to be this direction, right? The height of the rectangle in that direction. So delta yj is going to be y sub j minus y sub j minus 1. And that's for j going from 1 to m, capital M. All right, and then the volume, so what we'll call maybe v sub ij, this is going to be the height, which is our value of our function at the test point. And again, the test point can be at any point inside this rectangle. So it's f of xi star yj star times the area of the ijth rectangle. That was supposed to be an A, sorry. So the area of the ijth subrectangle. So the aij is the area of rij in this notation here. All right. So in other words, the area is going to be delta xi times delta yj, right? For this rectangular example. All right. So this will be aij becomes delta xi times delta yj. Okay, so we need to then sum this up over all the rectangles. The rectangles extend in both directions though, right? And so what we end up with is a Riemann sum definition for our volume, which we're denoting our volume by this symbol, right? This double integral symbol. And so we define the following. We define the double integral over R of f of xy dA. We define this to be the volume of the solid above R. Above could mean below, right? So we know how this works, just like in Calculus 1, but determined by the graph of f, right? And then this is computed by this formula. So the double integral over R, f of xy dA. This is the sum. It's a double sum, actually. So sum as I goes from 1 to n, j goes from 1 to m of volume ij, right? So we wrote this right here, vij. We wrote this out. So on one hand, it's just vij. On the other hand, whoops, this is not equal yet. So I want to write both ways, though. It's approximately equal to this, right? So then, how are we going to work this out? Well, it's going to be I, 1 to n, sum j goes from 1 to m of all this. So now it's the function, f of xi star yj star times area of the ijth rectangle. And now, look at, you can see, right? You can see exactly how this works. You could call this delta aij. So now it looks like dA, delta A, right? Looks very similar. And so then, so the actual formula is this one. I'll put a box around this when we're done. But that's only an approximation, so how do we make it exact? Well, we take a limit, right? So it's going to be equal to, in some sense, a double limit, and I'm going to write it as a double limit. So limit is n goes to infinity, limit is m goes to infinity, sum I goes from 1 to n, sum j goes from 1 to m, f of xi star yj star, and then delta ij is delta xi delta yj, right? So for this scenario where we set this up on a rectangle and our function is continuous on the rectangle, etc., then this is exactly the definition, so we can compute it this way. All right, so this is our Riemann sum definition of a double integral of a function of two variables over a rectangle. So what I'd like us to do now is take a few moments to use the Riemann sum definition to compute a double integral for us. All right, so use the Riemann sum definition. That's exactly what I've just written down, right? What we've just defined. Use the Riemann sum definition to compute the following. Double integral over R of, the function in this case is going to be x squared y dA, where, so this doesn't mean anything if we don't know the rectangle, right? You have to know the rectangle for this to be meaningful. And so in this one, the rectangle is going to be given by, it's a very simple rectangle, so 0, 3, cross with 1, 2. So 0 to 3 in the x direction, 1, 2 in the y direction. So take a few moments just to review your Calc 1 Riemann sums. Take a few moments, work this one out on your own, and then when you come back, we can work it out together and investigate a little bit more on double integrals. All right, let's see how you guys did. The first thing that we need to do is break this up. Well, let's write out the definition, and then we can look at the pieces that we're going to need to define and break up. But remember, the definition is it's exactly this, right? So let's write it out with our function in here. So our function of xi star yj star, this is going to be xi star quantity squared times yj with a star. All right, so that's all we have to do. So what do we need, right? So we need a couple of things. We need our partition. Let's say we're going to choose uniform partitions. And then we need our test points, right? We need our test points. And then we'll be able to plug in and hopefully compute the limits as well. All right, so let's see how this goes. Our uniform partitions, we can choose these by choosing basically the number of partition points, right? So let's say we're going to fix n and m and put the following. So delta x sub I will just make constant. That's the uniform part, right? So delta x. So this one's going to be like beta minus alpha over capital N, which in this case is going to be 3 minus 0 over n, or just 3 over n, right? And then same thing with delta y sub j. That's going to be just constant, delta y. That's going to be delta minus gamma over m. So that one's going to be 2 minus 1 over m, or just 1 over m. All right, so there's part of our uniform partition. These are just our constants here. Our constant delta x and delta y. Then we also need our test points. So the test points we can choose, again, from the uniform partition to be the right endpoints. So xi star can just be our left endpoint plus I times delta x, right? So it can be alpha plus I times delta x, just like we would do in Calc 1. Alpha is 0, right? I is the index here, and then delta x is 3 over n. So xi star is just 3i over n. Similarly, y sub j star, this is going to be our delta plus j times delta y. Delta is 1, that's the lower bound in the y direction, plus j over m, right? J times 1 over m. And that's our yj star. So that's it for that one. And now we need to plug all of this into the function, right? So f of xi star yj star, this is going to be 3i over n quantity squared times 1 plus j over m. We don't actually have to multiply this out, like distribute this out, this part, and we'll see why, but this one is going to end up being 9 I squared over n squared times 1 plus j over m. And then let's write down our Riemann sum, right? So the double integral now, r f of x, y, dA. This is going to be the limit as n approaches infinity of the limit as m approaches infinity. Sum I goes from 1 to n, j goes from 1 to m, right? Of this function, so 9i squared n over n squared times 1 plus j over m times delta x, 3 over n, times delta y, 1 over m. Okay, so this is what we need to compute now. And now we notice that the i's and j's can actually be separated in this equation. So the terms that are going to kind of mix here are going to be the I terms and the j terms. So the I terms that have the n's, right? Anything with an I and an n can be kind of grouped together, and then everything else should just have an m or a j. And because of the way sums work and the way that limits work, we can rearrange this and write this as actually the product of two different limits, okay? So this is now going to be the limit as n approaches infinity of the sum, I goes from 1 to n, and then the limit we're taking now, this is going to be 27i squared over n cubed. All right, we'll deal with that in a minute, right? But that's been simplified. And then the other one is going to be, we're multiplying here. We're just rearranging, right? Factoring in some sense. But it's still multiplication. So this is then the limit m approaches infinity. Sum j goes from 1 to m of, this is now going to be parentheses, again, 1 over m plus j over m squared. And there's the whole, that's the whole thing for the second one, right? All right, so let's look at these individually then. The first thing that we can do is we can deal with each of these summations. You have to do the summation before you do the limit, right? So with this first one, we have the limit as n approaches infinity. The summation only cares about the I. So this 27 over n cubed can come out, and then the summation that's left is I from 1 to n of I squared. And there's a formula for that, which you probably remember. This one can be distributed out, and we can do the same thing with the second one, right? So this one's going to be the limit, with both of them actually, the limit as m approaches infinity. 1 over m can come out. This one's left with sum. This one, we're going to need parentheses here, okay, or bracket here. But sum j goes from 1 to m of just 1. And then the plus here, limit m approaches infinity. This time a 1 over m squared comes out. And now we're left with the sum. J goes from 1 to m of j. And so at this point we need to remember how these work, right? We need to remember the formulas for each of these summations. So let's put parentheses here too, just so we don't get mistaken. So I'm going to write over here our formulas. So we have sum. I goes from 1 to let's do this with like a different letter. Let's say k of 1. This is just adding 1 plus 1 plus 1 plus 1 all the way up k times, right? So this is just going to be k. Sum I goes from 1 to k of I. This is 1 plus 2 plus 3 plus 4 up to k. This one is k times k plus 1 all over 2. All right, and then this one, I goes from 1 to k of I squared. You should remember these from Calculus 1, I hope. But this one's going to be k times k plus 1 times 2k plus 1. This one's all over 6, actually. All right, so we're going to use these now. We're going to plug these in where they belong. So let's again color code these with a highlighter. So this orange one is k. That one is just of 1, so that one goes here. So that's going to be in this spot, right? We got one of each. That doesn't always happen, but this one, where you're adding up just the I, in this case is j, that one's going to go in this spot, right? And then finally, we've got this one, I squared, that one's going to go here. All right, and then we just have to put in the appropriate upper bound for the given problems, right? So we're almost there. This one's now going to be the limit as n approaches infinity. 27 over n cubed times n times n plus 1 times 2n plus 1 all over 6. And then times the limit as m approaches infinity, 1 over m times m. So that one's just m, right? Plus the limit as m approaches infinity, 1 over m squared, and this one's going to be m times m plus 1 over 2. And notice that now we've just got our limits here, and we just very carefully compute these limits. This one's going to be 27 over 3, which is 9. So, you know, verify this. Pause the video if you have to, but verify that one's going to end up being just 9. This next one is 1 plus this one is a half, right? So this next one is a half. So this ends up being 9 times 3 halves, or 27 halves. So that's the answer. All right, so that's by using the Riemann sum definition, kind of a double Riemann sum. One Riemann sum in the I variable, right? One in the J index, I should say, or the X variable, the Y variable. You're able to compute them. Sometimes you can't separate them out like this, but you can still compute them one at a time and then do the other one. In this one, we were able to just kind of separate them out and do them and multiply them all together. But let's also check something else. So we know how to take partial derivatives, right? So let's check that we could compute this integral by actually doing what you might call partial integrals. So let's try something here and just see what happens. Remember, it was the double integral over r of x squared y dA, where our r was the interval 0, 3 crossed with the interval 1, 2. All right, so let's try two things here. We've already computed the exact answer by Riemann sum, right? And so now let's try to compute what's called an iterated integral. So we'll first compute on the inside the integral from 0 to 3 x squared y dx. And then after we've done that, we'll compute the integral from 1 to 2 of whatever that answer is, dy. So how are we going to compute this integral 0 to 3 x squared y dx when there's a y in there? Well, just like we do with partial derivatives, we're going to treat that y like a constant when we're integrating with respect to x. So this is like a partial integral, you might say. All right, so how do we do that? Well, we know how to compute by the fundamental theorem of calculus, right? These definite integrals in terms of antiderivatives. So we just integrate, basically. We find the antiderivative with respect to x. So that's going to be 1/3 x cubed times y evaluated from 0 to 3, right? And then that's x equals 0 to 3. So this is where it's good to remind yourself what the variable is. X is going from 0 to 3 here. So this x tells us that these are x values, right? And then we can compute. We plug in. So this is from 1 to 2. When we plug in 3, this is 27 over 3, so 9. So that's going to be 9y minus 0. So this just ends up being 9y dy. And then this is just a regular Calc 1 integral, right? And so this is going to end up being 9 halves y squared evaluated from y equals 1 to 2. All right. 4 minus 1, that's 3. So look what we get. 9 halves times 4 minus 1, that's exactly 27 halves, right? 27 halves. So we got the same answer. All right, what if we did the iterated integral in the other direction? What if we started on the inside with the y integral, right? And then after we did it, integrated with respect to x. Let's find out. So this time we're going to treat the x squared like a constant. We're going to leave this 0 to 3, this integral on the outside. When we integrate with respect to y, we get 1/2 x squared y squared. And now we're plugging in y equals 1 and 2 into this one, right? dx. We have to evaluate that before we can integrate the next integral. And when we do, we get what? We get 4 over 2. So 2x squared minus a half x squared. So 2 minus a half, right? So that's going to be 3 halves. So 3 halves x squared dx. But yeah, make sure you write that out if you have to. But it's going to be 4 over 2, which is 2, 1 over 2, which is a half. So 2 minus a half. That's right. All right, and so then we integrate one more time. Now when we integrate, this just becomes what? 1/2 x cubed. So this is 1/2 x cubed is evaluated from 0 to 3, and 3 cubed is 27. So this is also 27 halves. All right, so Riemann sum definition. We found it was 27 halves. Iterated integral method. These are called iterated integrals. Iterated integrals. All right, for these iterated integral methods, we got the same thing, right? And so this leads us to kind of a version of the fundamental theorem of calculus for rectangles, at least for rectangles. So let's write down Fubini's theorem. This is item number 4. Fubini's theorem. So Fubini's theorem only applies to integrals over rectangular regions. I'm going to write it in terms of continuous functions, but like I said before, you can imagine, just like in Calc 1, that the functions don't have to be continuous to be integrable. But let's say in terms of continuous functions, because it's going to be the easiest way for us and the most likely way that we're going to use this, all right? But let's say this: if f is continuous on the rectangle R, which we're writing in this notation, so alpha, beta, that's the x values, crossed with delta, gamma, that's the y values, then the following is true. The double integral over R of f of xy dA. So this is the, by definition, this is defined by our Riemann sum, right? But this is equal to the iterated integral in either direction. So alpha to beta, f of xy. This is doing dx first, then dy. So this is an iterated integral just like I wrote up here, except I didn't put the parentheses. Okay, you don't have to write the parentheses. You can if you want to. Fubini's theorem says this is also equal to the integral in the other direction. So where you do the y direction first. So dy dx. Now, when you don't write the parentheses, you still work from inside out. So closest to the function starts, right? So even though there's no parentheses here, this one, since it says dx here, it's telling you that the boundaries of the first integral are the x values, and the outer one are the y values. Same thing here. This one, the inner one, those are the y values. The outer one, those are the x values. All right? So that's Fubini's theorem. So now let's try to use Fubini's theorem. So we just did an integral like the hardest way possible, or at least the most tedious way possible, by Riemann sum, right? And then we did this iterated version. So here, if you're given a problem that says to compute the double integral over R of y times sine of xy dA, that's a y, then number one, it doesn't mean anything until we're told what the R is, as usual, right? But R here is going to be a rectangle from 1, 2 in the x direction, 1 to 2 in the x direction, crossed with 0 to pi in the y direction. All right, so compute this one. We know that sine is continuous, right? Multiplying by polynomial functions, continuous. So this is going to be a continuous integrand. So why don't you guys take a moment and think about how you can use Fubini's theorem to compute this one. Try to get an answer, and when you come back, we'll do it together. All right, let's see how you guys did. Fubini's theorem says you can go in either direction, so some directions are easier than others, right? Let's start by writing this out in the y direction. So let's say the first we would want to do is the integral from 0 to pi in the y direction, y times sine of xy times dy dx, the way I've written it. Now, there is theoretically nothing wrong with this, right? When you write this, you look at this. We know how to integrate this. This has to be done by integration by parts, right? So this requires integration by parts, which is not a big deal. But when you see that, you might ask yourself, you might say, oh man, integration by parts is, a chance for me to make a mistake, right? It's another chance for me to make a mistake and do something wrong. So why don't I try to swap the order of integration and do this one in the other direction first? So the other direction would say, by Fubini's theorem, right? By Fubini, we can also do this one in this order and get the same answer. So integral from 1 to 2 first, of y times sine of xy dx, and then in the y direction. So now when we start in the inside, we're going to integrate with respect to x first. We're going to treat y like a constant, right? So the antiderivative of sine of u is 1 over u, negative 1 over u, cosine of u, right? So that's not exactly right. So what I meant is if it's a constant, right? So the y is a constant. So we're going to have a 1 over y. So let me write this out. This is going to be equal to integral from 0 to pi. And then inside here, what we have is antiderivative, right, is negative. This y is still here. Divide by y from this antiderivative, cosine of xy. Evaluated, x equals 1 to 2. All right, so there's the antiderivative with respect to x. We evaluate it, and we are going to get, this is going to be now the integral from 0 to pi of, what's it going to be? It's going to be negative cosine of 2y plus cosine of y dy. All right, and so we can now easily do this one, right? So antiderivative of cosine is sine, so this is negative 1/2 sine of 2y plus sine of y. Y goes from 0 to pi. And we plug this in. Sine of 0, sine of 2 pi, those are the same. This one's just 0, right? That's gone. This is going to be sine of pi minus sine of 0. That's also 0. All right, so sine of pi is 0, sine of 0 is 0. Sine of 2 pi is 0. Everything's 0 here. But it's definitely easier to compute this one in the x direction first and then in the y direction to get your answer. It's not a bad exercise just to remind yourselves about integration by parts to do this one in this direction first. Make sure that you also get 0 going that way. All right, so there's an example of iterated integrals using Fubini's theorem. So let's talk about another type of integral. We actually already saw this one, this kind of integral. Well, let's suppose that we have the following integral. Let's suppose that this is x times integral over a region R, rectangle R, x times y plus 3y minus 2x minus 6 dA. So you can put parentheses here if you want. And this one, R is equal to 0, 3 crossed with 1, 2. So similar, the same interval, the same rectangle that we had before, but a different function now. And we want to integrate this, so we could do this term by term. Or what we can notice here is that actually this term right here can be factored. So we can notice that x times y plus 3y minus 2x minus 6, this can be factored to be x plus 3 times y minus 2. And so if you multiply that out, you'll see that that is exactly the same thing, right? So it's exactly the same. And so here's what we can do. We can take our integral over r, x plus 3, y minus 2, dA, that's the same as this, right? And write it in iterated form here. So integral, I'll do it, it's not going to matter, as we'll see here. But the way I wrote it, it's got dy inside and dx outside. And then because, so if we're doing this by iterated integral, right, then we're doing this integral first with respect to y. Because that's with respect to y, notice that this term does not have any y's, right? So this can be kind of factored out. Only out of the first integral, though, but this can be written as integral from 0 to 3 of x plus 3 times the integral from 1 to 2 of y minus 2 dy, all times dx. But now this one, so now we apply the same logic, but this term right here does not depend on x, right? And it's inside of an integral with respect to x. So that one can kind of jump over here. And we can actually write this one as a product of the integral from 0 to 3 x plus 3 dx times the integral from 1 to 2 of y minus 2 dy. This is called a separable integral because we can separate the x and y variables and just compute two integrals, two Calc 1 integrals independently, and then multiply the values of those two integrals to get the value of the single double integral, the one double integral. All right, so let's do it. This one's going to be 1/2 x squared plus 3x evaluated from 0 to 3. And this one's going to be 1/2 y squared minus 2y evaluated from 1 to 2. So this one's 9/2 plus 9. And so that's going to be 27/2, right? So 9/2 plus 9 is 27/2. And then this one is going to be 2 minus 4, so negative 2. And then minus 1/2 minus 2, so that's plus 3/2. So that whole thing's a half, right? Negative a half. And so then when we multiply this together, we get negative 27/4. So check my work there, but negative 27/4 just by multiplying those together. All right, so the last thing that we'd like to do in this lecture is talk about how to deal with regions that are not rectangles. Okay, so let's call this general regions, but really they're not going to be as general as you think here. But double integrals over general regions. So the idea here is going to be the following. We are going to break this up into two types. So we're going to say we have type 1 integrals and type 2 integrals, just to be able to compute them. So when I say general, I just mean more general than a rectangle. But the first one, the type 1 regions, these are going to be regions that are bounded between two curves in the x direction. All right, so let's let y equal f1 of x, and I said the x direction, I meant the y direction. So f1 of x and y2 equal f2 of x. Whoops, just y. It doesn't have to be y2. But y equal f2 of x. Let these be curves that bound a region D between, so they bound them in the y direction between x equals alpha and x equals beta. And so what do I mean by that? Well, let's look at the domain here. So the domain space, again, is the xy plane when we say domain. So we still have our alpha and our beta, and these are still going to be kind of vertical boundaries in this direction. But the curves, the boundaries of the region in the other directions might look like this. So these are bounded by functions in this direction. So this one up here would be y equals f2 of x. This one would be y equals f1 of x. And the region in this scenario is bounded in between the two blue curves and then also in between the red boundaries. So this is the region D. This is called a type 1 region. So type 1. This region is type 1. So what I really should have done here, instead of shading it this way, I'll do it in a different color now, is shade it this way. So we are still going to chop this up in this direction. All right, but what we're going to do, basically, I'm just going to go through this very quickly, is we are going to assume that we have a larger rectangle, R, that shares the same left and right endpoints, alpha and beta, but that goes from, say, delta up to gamma in this direction. All right, so we can always find something like this if our region is type 1. So suppose R is a rectangle. So in this case, alpha beta, that's the same as our integral, crossed with delta gamma. That's different than our boundary, but it's going to contain, right? That contains the region D. Then what we're going to do, we want to integrate our function f on this region. So we want to integrate our function f of xy on this region. What we're going to do is define an extension of a function. So this is where I was talking about before that we don't need continuous, right? We need basically piecewise continuous. And we're going to define our function to be 0 outside and little f inside. All right, so we're going to define, like I said, this function big F of xy. So let's call this region du for upper and dl for lower. And then region D is in the middle, right? So f of xy we're going to define to be 0 on d upper. It's going to be equal to little f of xy on d, actual d, and it's going to be equal to 0 again on d lower, so the part that's below, below d. All right? And then we know how to integrate this, right? We know how to integrate this. So then let's compute the integral, the double integral, over the rectangle R of this function big F of xy dA. This can be broken up into pieces, right? Just like any integral in Calc 1, you can break it up into the integral over region d sub L, plus the integral over the middle region, plus the integral over the region d sub U. So this will be the double integral over d sub L of 0 dA. That's what it equals, right? Big F equals 0 on d sub L, plus the double integral over d of f of xy dA, little f, plus the double integral over d sub u, you see how this is going, of 0 dA. And the two integrals that are equal to 0, of course, when the 0 is the integrand, I should say, the integral itself is going to be equal to 0. And so what we end up with is that the double integral here over d of little f of xy dA is the same as the integral of big F on the rectangle, the entire rectangle, right? So what we can do then, what this basically tells us, is that what we're allowed to do is we can cut this in vertical strips, as I've indicated here with the magenta strip, right? And we can use a test point, which we're not going to do a Riemann sum actually when we compute it, but the idea is you pick a test point where you compute the lower bound and the upper bound of your rectangle, and you use both of the curve values to determine the height of your rectangle, all right? And so what we end up doing then is we end up integrating in the y direction from our test point below to our test point above, and then we have our delta x, right? And so because of this, we have to integrate in the x direction first so that we can get our limits using our test points and then integrate in the y direction. All right? So let me show you how this works then. So for type 1, a type 1 region D. Whoops. Then the integral is going to be the following. Double integral over this type 1 region, f of xy dA. It's going to be, like I said, we need to integrate I think I said it wrong actually. We need to integrate the y direction first, right, to get our boundaries, and then we can plug in the x's to the test point. So we need to integrate from the lower bound f of x1 up to the upper bound f of x2 of the function f of xy dy. That's going to put x's in for the y's. So then this will just be a function of x, and at that point we can integrate from alpha to beta dx. So we're allowed to have functions in the boundary as long as it's the interior integral, the inside integral. The exterior integral has to be numbers, right? Because this has to be a definite integral. So this is the formula for a type 1 integral. We just bound, if the region is bound by curves in the y direction, we integrate those out first, get the x's in there, right, for y, and then integrate everything with respect to x. All right, you can probably guess then that a type 2 region is just going to be the same, but a type 2 region is just going to be bounded in the other direction. So type 2 is bounded by functions x equal to g1 of y and x equal to g2 of y. So a type 2 region is going to look like the following here. There's our x, there's our y. So this time we're going to be bounded between our delta and our gamma here. So the entire region has to have flat, like a straight line edges in this direction. And then maybe the functions that bound the other look like this. Maybe it looks even like this, where they share a point over here on this side. But then this region right here, this would be a type 2. Type 2 region. So this curve, maybe I should have drawn them slightly different colors. This one is going to be x equals g2 of y, and then this one is x equals g1 of y. All right, and so the formula here then is that the double integral over this region, d f of xy dA, for a type 2 region, it's going to be, all right, integrate in the x direction first, so go this way first, right? And so you're going to be bounded between g1 of y and g2 of y. And when you plug these in, this will change the variable so that only y is left, and then you integrate out from delta to gamma in the y direction to get your final numerical answer. All right, so let's do a couple of examples to end this lecture, but this is how we deal with our general region. So this is item number 8 of the lecture. Let's integrate over region D, function xy dA. And I want to do this where D is bounded between the following curves. So the curves are going to be the line y equals x minus 1 and the parabola y squared is equal to 2x plus 6. All right, so this is going to be in the xy plane. I'll help you sketch it. XY plane. One of the boundary curves is the line y equals x minus 1. So that's a line with positive slope and negative 1 for the x-intercept. Positive 1 slope, I should have said. Right, so there's that line. The other one is going to be a parabola. So we probably want to solve this for x, right, because it's y squared. So if we rearrange this, this one's going to be what? So I'll just do it in 2 steps, but 2x is equal to y squared minus 6, so x is equal to 1/2 y squared minus 3. So that tells us that negative 3 is the vertex. So let's just plot this in green. So negative 3 is the vertex, and then it opens at a rate of 1/2 here. I'm just going to draw it, and then we can, it doesn't have to be perfect, but it's going to open like this. Okay, so there's the green one. This is the blue one. The blue one's the line, obviously. And then the region is bounded between them. So the region is bounded between them. I'm going to shade it. All right. I don't want to mess anything up here. But there's the region right there. That's the region. So this is D. All right, so you guys are going to have to find, this is, remember, this was at negative 1. You're going to have to find these 2 points for sure. It might be helpful to find this point, maybe. But definitely these 2 points, you're going to have to decide whether to do it as type 1 or type 2, and then write your iterated integral with your functions in the inner boundaries, potentially, and see how it goes. And I'll check in with you guys when you're done. All right, let's see how you did. First of all, this one definitely looks like it could be either version, but notice that if you were to try to do this as a type 1, if you draw this vertical line here, this side is type 1 perfectly fine, right? On this side, to do it as a type 1, you can do it, but you have to think of this curve right here, this green curve, as both the upper and the lower bound in the type 1. But you definitely have to cut this into 2 different type 1 regions if you're going to do it as type 1. So like a D1 and a D2, integrate them separately, and it's perfectly fine. You can do it that way. However, if you do this as a type 2, then you can do it by just going this way, right? Type 2, then you're going to be going from the green curve to the blue curve, right, in both cases. So as a type 2, this just needs one integral, right? So this will go from, in the lower bound will be x equals the parabola, which was, remember, 1/2 y squared minus 3, to the line, which is x equals y plus 1 if you solve this for x, right? So I think that's what we should do, right? Do it as a type 2. So once we do that, then what do we need to know? Well, then we need to know the y values of these 2 points right here, because we need to know where to integrate from. Those are our boundary points. This is going to be our delta, and this is going to be our gamma up here. We need to find those, right? So those are the y values where the 2 curves intersect. Well, look at, we just solved both of these for x. We can set them equal and find out exactly what the y value is. So let's do that next. So this is going to be 1/2 y squared minus 3 has to equal y plus 1. We can multiply through, right? This is y squared minus 6 equals 2y plus 2. Get everything on the same side. Y squared minus 2y minus 8 equals 0. And this is a quadratic equation that factors, right? So it's going to be y minus 4 times y plus 2. Right? If you multiply that out, you get this back. So our values are y equals 4 and y equals negative 2. And you can tell which one's which, right? Negative 2 and 4. Those are the y values only. We don't need the values of the whole point, right? We just need the y values because that's where we're integrating. But that's our delta. So this one's our delta, and this one's our gamma. All right, now we just have to integrate. So the double integral over d. Now the function comes into play, right? The integrand, xy dA. We're going to compute this as the integral. The outer integral is from negative 2 to 4. The inner integral is, as we said, 1/2 y squared minus 3 up to y plus 1 of x times y. This is in the x direction first, and then the y direction. So we iterate. The outer integral hangs out and waits, right? The inner integral is going to be 1/2 x squared times y. Whoops, 1/2 x squared times y, where x goes from, again, our parabola, 1/2 y squared minus 3 up to y plus 1. And then we'll do dy. And now it's just a whole bunch of algebra, actually. So down here I'm going to write 1/2 x squared times y, evaluated from x goes from 1/2 y squared minus 3 up to y plus 1. We just need to work this out. So that's going to be that minus 1/2 y plus 1 quantity squared times y. And very carefully work this out. So 1/2, this one is 1/4 y to the 4th. This one's going to be minus 3y squared plus 9, all times y, minus 1/2 y squared plus 2y plus 1, and then times y. Multiply everything through again. So we get 1/8 y to the 5th power minus 3/2 y to the 3rd power plus 9/2 y minus 1/2 y cubed, right? Minus y squared, and then minus 1/2 y. And then we can combine like terms. So 1/8 y to the 5th minus 3/2 minus 1/2. So that's minus 2. Right? Minus 2y cubed. Then we have our minus y squared. And then we have plus 9/2 minus 1/2. So that's going to be plus 4. It's going to leave us with just plus 4y. So that's just the integrand, right? So that's actually the most work we have to do, because now we plug that in to the y integral. So the answer to our double integral over d of xy dA is now going to be the integral from negative 2 to 4 of this function. 1/8 y to the 5th minus 2y cubed minus y squared plus 4y dy. All right? So this one's 1/48 y to the 6th minus 1/2 y to the 4th minus 1/3 y cubed plus 2 y squared y goes from -2 to 4. All right, 4 is 2 squared, right? So when we plug this in, this is going to be 1 over 48 times 2 to the, let's see if any of this will cancel here. I'm not sure if it will, but we can just try. So this will be 2 to the 12th, right? 2 squared. Yeah. Minus 1/2. This is 2 to the 8th. Minus 1/3. 2 to the 6th plus 2 times 2 to the 4th. Jump the gun there. Minus, this one's going to be 1 over 48 times 2 to the 6 minus 1/2 2 to the 4th. This one's going to end up being plus 1/3 2 to the 3rd, and then plus 2 times 2 squared. All right, so I took some time and just typed this in a calculator because this is getting a little messy here, but this one ends up being, after some careful calculation or maybe help from a computer, ends up being -92/3, so, or -30.6 repeating, -92/3. So that is the answer to this integral. So hopefully that's what you guys got. All right, let's do just one more. This one, I'm going to start by drawing a picture of the region. So this time the region is going to be given as follows. So let's say this is the x and the y. And we've got a couple of points here. So this is 1, -1, -1. And our region kind of is bounded by this type of shape. These are supposed to be straight lines. So yeah, here's our region again. These are curves over here. All right, so there's the region. This curve right here is given by x equals y minus y cubed, and this one right here is given by y equals x plus 1 quantity squared. And so what I would like you guys to do, this is the region D. What I'd like you to do is compute the integral over this region of just y dA, just the integral y dA. To do it, you're going to want to break this one up into a couple different subregions. So I would break it both here and here, and break it into three subregions, and then treat each one separately, and then add them up. Okay, so if we call this D1, D2, and D3, then the integral here is going to be the double integral over D1 of y dA plus the double integral over D2 of y dA plus the double integral over D3 of y dA. All right, so take some time, work that one out, and I'll check back in with you soon. All right, let's see how you guys did. On this one, let's break it up exactly as we said here. So the region D1, this one's going to be bounded between x equals -1 and then x equals this formula, right? Y minus y cubed. And then similarly, the y on this region, the y is going to be bounded from -1 up to 0. So this all right here is the bounds for D1. For D2, the bounds are going to be, so now we've got a type, that by the way, that was type 2, right? That was a type 2 region. Now we've got a type 1 region. So this one's going to be bounded from y equals 0 to y equals this x plus 1 quantity squared function in the x direction, or sorry, the y direction as type 1. And then the x is going to be bounded from -1 over to 0. And so that'll give us this region. And then finally, our D3, this one is again going to be type 2. It's going to be bounded from y equals 0 to from x equals 0 over to x equals y minus y cubed, right? It's type 2. X equals 0 to x equals y minus y cubed. And then the y is bounded from 0 to 1, right? It goes from 0 to 1. All right, and so we write out our three integrals now. So this one's going to be -1 to 0 on the outside. -1 to y minus y cubed, y dx dy, plus, this one's going to be the integral, -1 to 0 on the outside. Inside is going to be 0 to x plus 1 quantity squared, y, this one's dy dx, plus this next one bounded from 0 to 1 on the outside, 0 to y minus y cubed on the inside of y dx dy. All right, and now we just compute. So this one's integral -1 to 0. Integral of y dx is just going to be x times y, right? So this is x times y, where x is -1 up to y minus y cubed dy. And so -1 to 0. This is y squared minus y to the 4th, and then plus y dy. So that'll be computed. This next one, -1 to 0. This integral is 1/2 y squared, and then plug in x squared, right? So this will end up being 1/2 x plus 1 to the 4th dx. So that one was straightforward. And then same thing here, right? This one is x times y. We're only plugging in this and then a 0 on the bottom. So this one we've done most of the work. 0 to 1. This one's going to end up being y squared minus y to the 4th dy. All right. And so this one I'm going to shift actually. So this is 1/2 x plus 1. So I'm going to make a change of variables and swap this out for like a u. So let's let u equal x plus 1. Then du is just dx, right? No problem there. But then u of -1 is 0, right? And u of 0 is 1. So this one becomes 1/2 integral from 0 to 1 of u to the 4th du. And that's going to be much easier to compute. We can do it in our head, right? After we make that change of variables. So this one's going to be, we can write it all out here. Just go in order again. We're just going to go to this and then over to here. But this one's going to be 1/3 y cubed minus 1/5 y to the 5th plus 1/2 y squared. Y is going from -1 to 0. This one's going to be plus 1/10 u to the 5th, 0 to 1. And then this one's going to be plus 1/3 minus 1/5. That's it, right? 1 to 0. This one's just 1/10. So we don't have to need to, we plug in the 1 to 0, we're done there. These ones we have to plug in because it's going to be a 0 and a -1. So this one's going to be 0 minus a -1/3. So that's 1/3. This one's going to be 0 minus a negative and a negative, right? So this is going to be plus, it's going to be minus, 3 minuses. Minus from here, minus from here, minus from here. So minus 1/5. And then this one's going to be truly minus 1/2. And here we have everything else. We have our plus 1/10, our plus 1/3, and our minus 1/5. All right, so this is now 2/3 minus 2/5 minus 1/2 plus 1/10 All right, I think the common denominator is going to be 30 here. So this is 20 minus 12 minus 15 plus 3 all over 30. And so this is going to be, what, -7, -4, 30 is -2/15. So there we go. Should be -2/15 for that one. All right, let's leave this one here. I hope this this all makes sense. I know some of the calculations with the fractions and the numbers got a little messy at the end here. But hopefully the main ideas of how to set up the integrals, that's the most important part, how to set up these integrals. Both of these last two examples, how to set them up is by far the most important. Computing them is also important, but computing them, you know, we can get help from calculators and computers and stuff. Setting them up, though, we have to be able to do ourselves. So, like I said, I'll leave this lecture here, and I'll talk to you guys in the next one.